Okay, welcome to the freezing point depression lab for Chem 1225. And this lab is one of the simpler ones. The equations that we're going to be dealing with are really simple, but in this introduction I will go into a little bit more depth than you really need, just because I think it makes the lab more interesting if you understand why things are happening the way they are happening. But the basic idea for freezing point depression is that if a solvent freezes at one temperature when it's a pure solvent, if you add any solute to it to make it a mixture, then the freezing point will go down. So pure water, for example, freezes at 0 degrees Celsius. If you add an amount of salt to the water, then it will actually freeze at a lower temperature, maybe -1 or 2 degrees Celsius. And so the equation for how much the temperature goes down is that delta T is equal to K F M. So your change in the freezing point temperature is equal to Kf is the freezing point depression constant. So each solvent will have its own value for Kf. Part of this lab is that we're going to be determining the freezing point depression constant. And then M here is the molality of the solution. And this is maybe the only really tricky part about this lab. Molality is a little bit different than molarity. And so what we have is the moles of solute particles over kilograms of solvent. Not the total kilograms of solution, but the kilograms only of the solvent. And this is what is the molality. And it seems like kind of a strange concentration unit when you first encounter it, but molality is actually really useful because both of these quantities depend on the mass or the number of particles, and so they're independent of temperature. If you think about how a solution will expand as the temperature increases and contract as the temperature decreases, that makes molarity a temperature-dependent concentration unit. You could prepare a solution that is precisely 1 molar in concentration, and then the temperature changes and now it's more or less than 1 molar. Well, molality will be constant across temperature changes. So that makes it convenient. And then also just the sort of the mechanism behind freezing point depression actually depends on the ratio of solvent and solute particles. And so molarity ultimately would be the inappropriate unit to use anyway. There is one interesting thing here. We're talking about solute particles. Now if we think about the way that things dissolve, that can introduce a little bit of complexity. If I have something like sugar, C12H22O11, that is table sugar, and I take solid table sugar and I dissolve it in a solution of water, then what I'm going to end up with is C12H22O11 aqueous. The individual water molecules become surrounded by water and they're solvated. Nothing too fancy there. But if I take something like NaCl solid, that's table salt, and I put that in water, then I'm going to get sodium plus ions and Cl minus ions. When they're in solution, they aren't actually stuck together at all. They break apart. Each of them is surrounded by its own hydration sphere of waters. And so what we really get here is 1 mole going to 2 moles of solute particles. And we can look at other things like, say, magnesium hydroxide, and that's going to form Mg2+ aqueous plus 2 OH minus aqueous. So this would go from 1 to 3. And basically what that means is, let's suppose I take 1 mole of sugar and dissolve it into 1 kilogram of solvent, then that would be a 1 molal solution. If I take 1 mole of sodium chloride, however, that produces 2 moles of solute particles, so that would be a 2 molal solution. And 1 mole of magnesium hydroxide would produce a 3 molal solution. And so the number of particles that are produced upon solvation can dramatically affect the molal concentration. You need to take that into account. Okay, so now I'm going to go into a little bit of detail about freezing points, and don't worry if you aren't wrapping your head entirely around all of this. This is a little bit of extra that I just thought you would appreciate. Okay, so we can draw a graph like this where the y-axis is the temperature, and then the x-axis is going to be the mole fraction of one of the 2 components in a mixture. So let's suppose we're making a graph of ethanol mixed with water. Over here we would have pure ethanol. Over here you would have pure water. And then everywhere in the middle is some ratio. Right in the middle would be half and half. This would be like 3/4 ethanol, 1/4 water. This would be 3/4 water, 1/4 ethanol. And what we can draw is a chart of the freezing points of these different solutions. So water has a freezing point at 0 degrees Celsius. I'm not sure what ethanol's freezing point is, but it is lower than water's. So this is the freezing point for pure ethanol, and this is the freezing point for pure water. And a mixture of the two is going to look like this. So if I have pure water and I add some ethanol to it, then the freezing point is going to drop down, down, down. If I have pure ethanol and I add a little bit of water to it, then that freezing point is going to drop down, down, down. And the slope of these lines is going to be related to that freezing point depression constant. Of course, somewhere in the middle we need to transition between the two of them and things get complicated. But we'll be mostly dealing with these early regions where you have mostly a pure solvent with some relatively modest amount of solute added to it. Now, if you look at this, the freezing points of ethanol and water are pretty similar, but if we choose, I'll just draw a whole new chart here. If you choose something like, table salt in water, well, what is the melting point or the freezing point of table salt? Well, it's like 1,200 degrees Celsius, I think. Table salt doesn't melt easily, and that would put water way down here. And anyway, what that means is that the freezing point depression curve for most solid solutes in liquid solvents is going to be really asymmetrical. In either case here, when freezing occurs, I'll find that the solvent, whatever is the majority component, has frozen out to form a more or less pure solid. And then the solute is going to be more concentrated in the amount of unfrozen solution that remains behind. And so if I start with a solution of this composition and I begin to freeze it, then what will happen is the water will freeze out as pure water, and that will mean that we have less solute, and the molality will actually go up in the remaining amount of solution, and the freezing point will change over the course of that process of freezing. And eventually you'll reach this point right here, the eutectic point, and at that point now you'll have reached a minimum freezing temperature, and everything will freeze out together and it will remain there. But at least in the initial stages and perhaps through to the end, if your concentrations don't allow it to reach a eutectic point, then your freezing point will actually drop over the course of your freezing. This is kind of like distillation, and in fact you can use fractional freezing in order to purify things. When I do like science demonstrations for my family at family reunions, I don't have easy access to concentrated hydrogen peroxide. And everything is better when the hydrogen peroxide is more concentrated. And so I'll just go to the grocery store and I'll buy regular old 3% hydrogen peroxide from the pharmacy there. And then I'll dump it all in a pot and stick that pot in the freezer and come back a few hours later and lift out the water ice layer at the top, and knowing that what's left behind is now more concentrated in hydrogen peroxide than what I began with. It makes for a funner demonstration. So there's a practical example of how this phenomenon can be useful to you. Okay, so ordinarily I would sort of walk you through the practicalities of how to perform this lab, but since you won't be performing it yourself, I'll just end this lecture here, and I'll talk about the practicalities of how we perform this lab as I'm performing them for you on camera. So good luck. Okay, so here we have about 10 milliliters of cyclohexane. This is just an empty test tube and a beaker full of ice and water. We'll put the cyclohexane into the test tube and put it in our ice water beaker and start recording. We'll stir it kind of regularly using the thermometer probe itself. It's made out of metal, it's not fragile, and there's not a lot of room to get anything else down in there to stir with. Say stop this run. And we'll just do the next one right now. Start recording. You want to see what the frozen cyclohexane looks like. It looks just like regular water ice. You know what, based on how this looks, I'm gonna guess that that first test tube actually had some contamination in it. And so let's throw out that first trial. And we'll actually warm this test tube up and run a second trial with this test tube as well, because frankly this looks a lot more like what I was expecting for a pure substance. It could be that I'm not stirring quite as much as before, but I think with such a small test tube, the stirring isn't that critical, and this is definitely looking more like what I would expect. And now after the temperature had stayed really within almost a couple hundredths of a degree Celsius in the same spot for over a minute, it's now starting to drop again. So we'll let it go down till maybe about 5.5 degrees Celsius before we warm this up and try it a second time. Now there is definitely a more precipitous drop in the temperature. So we, at this point, have a completely solid cyclohexane sample. Look at it go down now. And you can see how it looks. Just like waxy and in consistency. It looks like solid ice water, but it feels waxy in consistency. So now I'm going to melt it back up. The warmth of my hands should be enough. I'll just hold this for a minute or so. We might as well stop recording. We can delete that first run. That's no good. Now it's mostly liquid, but I want to warm it up to where there are no little bits of solid floating around. And it looks like there we are. So I'll stick it in and we'll do now a second trial. we're now at the point where the temperature is dropping again. Although we'll let it run a little bit longer so that we can see a good clear shoulder in the data. So that is with the pure cyclohexane. The next part of this lab will involve a mixture of cyclohexane with some other substance. I chose naphthalene, which was one of the options given in your lab. So we'll go weigh out those quantities so that we can be quantitative about the molal concentration of our solution, and go ahead and make cooling curves for that mixture. Okay, here we have a new clean test tube. It's in a beaker just to support its weight, and we're going to measure about 15 milliliters of cyclohexane, but we need to know the actual weight delivered to the test tube. So we're going to tare the beaker together with the test tube of cyclohexane, and now we'll pour that 15 milliliters in. We'll let that settle, and you can see there the mass of the cyclohexane that we added is 12.445 grams or so. It's fluctuating a bit in that last sig fig. So we'll call it 12.445 grams. Set that aside and put on some weigh paper. Now we're going to weigh out an amount of solute that we're going to add. So like I said, this solute is naphthalene. Naphthalene has a formula weight of 128.16 grams per mole. Oops, sorry. I don't know if you can read that or not. It looks kind of fuzzy. But naphthalene, you can look it up and confirm that. And we're looking to get between 0.2 and 0.3 grams of this. So naphthalene is a solid. It smells like mothballs because indeed it is the primary ingredient of mothballs. Oh, you know what? That worked out nicely. A little bit inelegant how I dumped that in there, but that looks like it's about 0.23 0.233 grams. It's fluctuating a bit as well, so I'll let you determine how much that is. Now I'm going to try to be a little bit clever because we really care about the molal concentration here. It will be difficult to get complete transference of the naphthalene into our test tube. So I have tared it yet again to the weight of the test tube together with the cyclohexane. We'll add the naphthalene and do our best to get it all in that test tube, but inevitably some naphthalene will probably be sticking to this weigh paper. So let's just see how much we weigh here. 0.230 maybe, 0.230. So a slight discrepancy from what we weighed out before. We'll go ahead and use this number. Oh, I don't know, now it's climbing back up. 0.233. Anyway, that'll give you 3 sig figs at least. of the actual amount of naphthalene delivered to the cyclohexane. Now we have a mass of cyclohexane, a mass of naphthalene. We can use those to determine the molal concentration of this solution. Okay, so now we'll do the mixture of naphthalene together with cyclohexane. Oh, actually we better not. Looks like it hasn't quite dissolved all the way yet. That was almost a near disaster. The naphthalene is a solid, and it is soluble in cyclohexane, but you know, I didn't do hardly anything to mix these two. I just dumped it in, and that obviously caused problems. So I'm going to stir it until not only is the naphthalene fully dissolved, but until I'm kind of convinced that the composition is uniform throughout. What I really probably should have done was mix these two in a beaker where it's much easier to achieve good mixing, and then poured the beaker's contents into the test tube. I think this will do. And now you just get to see one way to deal with problem solving along the way in the lab. Okay, so I think we're there. Go ahead and put that thermometer in again, and as I'm stirring, I'm looking for signs of incomplete mixing. You should be able to see like wavy lines, like oil and water, if they're not mixed thoroughly. I'm going to say this is probably good. And let's get started with the cooling curve. Hold on a sec. There's just so much in here. It's like more than the height of my ice, so I'm just going to decant off a small portion of it. That shouldn't matter. It's the composition that matters, not the total amount. That'll make it a little bit easier here. Okay. Let's see how this goes. See, we've shot quite a bit past where the pure cyclohexane had frozen. I'm starting to see some crystals here. So there is some freezing that is occurring. There's definitely still some liquid as well. Getting past 0 anyway. We can go below 0 because I added some salt to the ice bath. And it feels like it's all solid right now. It feels like a waxy substance. And we're well below 0. We'll go ahead and leave that there for just a sec. So, you can see that this all went quite a bit quicker, perhaps because my salt ice bath is cooler, but there also wasn't as sharp and clear a distinction about where the phase transition occurred. In fact, it would be pretty difficult to even determine a melting point. We tried to keep an eye on when the crystals first started to appear, and we'll do another trial as well. So let's warm this up. Oh, I might as well stop taking data. We'll warm this up. Make sure it's all liquid. There's no floating bits. And we'll do this whole thing again. We're hopefully going to find is an inflection point where the slope begins to change. Here I am seeing crystals already. So I think that inflection point might have happened around 4 degrees. That'll be for you to determine. Maybe we'll even do a third trial because they're not that hard. And that'll give you 3 different ways to try and determine what that inflection point is. We'll go until we're below 0 again here. Oh. See, that really made a difference. I take the thermometer out and put it down somewhere else that was a colder location, and that definitely led to a spike there in the data. So let's do this one more time, and maybe on this last run I won't actually stir it at all. We'll see if that gives us better or worse data. These go pretty quickly, so it's no big deal to try it a third time. So we'll just melt it again. Make sure it's nice and warm. Okay. And we'll do one more trial here. Starting from a nice warm state, and I won't stir anything at all. We'll see how that looks. Or that's good enough. Anyway, so I will make sure I export the actual spreadsheets of these data for you, and you can look at the charts, look at the digits up here, and look at the actual data in Excel, whatever you think is going to be most reliable and convenient for you to figure out what your melting points are for the pure cyclohexane and for the naphthalene cyclohexane mixture.